Till now, what we have discussed is the classification of different types of heat exchangers. So now get in-depth analysis of each of these heat exchangers. First, let us go and analyze the temperature distribution profile of that, which is a very important parameter while analyzing the heat exchangers. So let us start with parallel flow heat exchangers. Here we will analyze the temperature profile of that. In the basic of parallel flow heat exchanger, what we have analyzed, that in the system, in the steady flow adiabatic system, both the fluid will be flowing in the same direction simultaneously. Okay, so let's do some of the analysis. Suppose this is a cross-sectional view this is a cross-sectional view of a heat exchanger. Supposing if this is a tubing tube type of heat exchanger, the hot red one represents the concentric, this is a concentric circle, pipe within a pipe, and we have seen the cross-sectional view. The blue color shows that it is the cold fluid, and the red color shows that in that annulus hot fluid is flowing, and both the fluid are flowing in the same direction. If we will visualize it in the lateral way, what we will see is that if this is the hot fluid that is going through, and this is the cold fluid that is going through, that means here cold fluid is getting inside the heat exchanger. From here the cold fluid is going outside of the heat exchanger. Similarly, here the hot fluid is getting in of the heat exchanger, and in this way the hot fluid is getting in of the heat exchanger, and here it is moving out. So let us draw this in a schematic way. This is the inlet cross section. Okay, let me use a different color to analyze that. So supposing if this is one cross section, inlet one, suppose this is another cross section, exit one, suppose. So hot fluid is flowing and simultaneously the cold fluid is flowing. Here the inlet cross section, suppose the x is equals to 0, and let the length of the heat exchanger be L, and the exit cross section, the x is equals to L. Then here what we analyzed, that the hot fluid is flowing, and simultaneously here what will happen, the cold fluid will also move. Suppose here it is the TCI and TC exit, and here it is THI and TH exit. So hot fluid is flowing in this way and cold fluid is flowing in this way. So this is what we come across to know from the heat exchanger analysis. This is what a parallel flow heat exchanger shows in a concentric way, in a cross-sectional view, and in a temperature profile. So here it is a length 0 to L. The fluid is moving from the inlet to the exit, and it will take some time to move from this way to this way. What this graph shows, that what much heat this hot object is losing, it is being gained by the cold fluid. So here if we will put the same mathematical equation to analyze this thing, what can I write over here, that mCp hot THI minus THE, it is giving this thing to mCp cold TCE and minus TCI. So here what is happening, what much heat is being given by the hot fluid is being absorbed by the cold fluid. Supposing if this mcp hot, that is the heat capacity of the hot fluid, is equals to the heat capacity of the cold fluid. Then what will happen? Supposing if this mcp hot is equals to mcp cold, then Thi minus The, that is this temperature difference, will be equals to this temperature difference. That means this type of temperature profile we will observe. So what kind of temperature profile this is, or for what case this is? If the heat capacity of the hot fluid is equals to the heat capacity of the cold fluid, then this type of temperature profile is observed. Supposing if mcp hot is greater than mcp cold, that is the heat capacity of hot fluid is greater than heat capacity of cold fluid. So you guys say this one is greater than this one. So what will happen if I will divide this one here? So this thing will go a ratio that is less than 1, obviously. So this factor will reduce. So in this case, so this one, this Thi minus The, how it will come? It will come as if so here it is Tci Tce, but here the Thi The. So what will happen? In this case, where the cross section moves from x equals to 0 to x equals to L, we can see the cold fluid take more time to extract heat, but the hotter fluid, the temperature gradient that is obtained is quite small as compared to the temperature gradient that is being given by this cold fluid. Now similarly, if we will move on to a case where this mcp hot is less than mcp cold, or you can say mcp or heat capacity of cold is greater than heat capacity of hot. In this case, what will happen? In this case, same way, the colder fluid that is transversing from the direction x equals to 0 to x equals to L, what will happen over here? The hot fluid will travel longer as compared to Thi, The as compared to the cold fluid. The cold fluid will travel a Tce, Tci. Hope I am clear about this concept, that when your mcph is equals to mcpc, the temperature difference is same. When mcp hot is greater, then this parameter, this Tce minus Tci, this ratio is getting lesser as compared to this temperature gradient, so it is coming in this way. And when mcpc is greater, and we'll differentiate, divide this with this hot one, then we will see that this is coming quite lower value, this trend is coming. Hope mathematically and physically the temperature profile for the parallel flow heat exchanger is understandable to you. If in GATE examination the question will come that if this is a temperature profile, what will be the heat capacity for the hotter fluid? When the so basically here this thing, what it shows you? It shows you the temperature gradient. You can draw the slope and you can say, okay, if this type of slope is there, my heat capacity of hot fluid is greater than the heat capacity of the cold fluid. If the slope is in this pattern, my heat capacity of the cold fluid is greater than the heat capacity of hot fluid. If both are going in the same way, that there is no change in the temperature difference, or both the temperature difference for the hot fluid and cold fluid are same, that means the heat capacity is same for both the cases. So here we analyze the overall thing for the parallel flow heat exchanger. Same case. Now let us move for a counter flow heat exchanger. So here we will analyze the temperature profile for the counter flow heat exchanger in the same way. So here also what we will see that if this is the cross section, now let's draw the cross section in a similar way. This is the hotter object annulus part in which the hot fluid is flowing, and this is the cold inner part in which the cold fluid is flowing. But here, as it is the counter flow, the direction will be opposite. So here, if I will go and plot a temperature profile for the system moving from the direction x equals to 0 to x equals to L, what I will obtain? I will obtain that in this case, what it will be? There it was the straight way and a curve as per the specific heat or the product of mass flow rate and specific heat or the heat capacity. Here what will be the thing? Supposing if here suppose it is the hotter one and here suppose it is the colder one. The colder one is flowing in the direction opposite to the hotter one. So here in this case THI, THE, TCIE and TCI. So in this case what you can see, it is nearly a straight line. Why so? Let's come towards that energy balance equation. mCp of hot THI minus THE is equals to mCp cold TCE minus TCI. Suppose this mass flow rate specific heat into mass flow rate product or the heat capacity for the hot fluid is equals to the heat capacity of the cold fluid, then THI minus THE is equals to TCE minus TCI. So this temperature difference is same, it's nearly a straight line. So here the condition is mCp hot is equals to mCp cold. Suppose we'll move along that your mCp hot is greater than mCp cold. So what will happen in this case? For the system x equals to 0 to x equals to L, if we will move, so here you will find the curve, it will be somewhat around a parabolic in nature, and here the thing is convex up. So here what will be the thing? Here if it is the cold fluid is flowing, suppose sorry, I did a mistake over here. Here what will happen? The cold fluid path is in opposite direction. Sorry, it's getting my mistake again and again. So yes, here, so it is TCI, TCE, and here it is THI and THE. So in this case, if mCp hot and mCp cold is there, it will be convex up. Here in this case, if mCp hot is greater than mCp cold or heat capacity of hot or fluid is greater than heat capacity of the cold fluid, the profile that will form, it will be of convex up. Similarly, if what we will move on to see, what will happen that when heat capacity of the hot fluid or the is less than the heat capacity of the cold fluid. For the same thing, for a distance x equals to 0 to the profile x equals to L, and here the thing will be THI, THE, TCI, TCE, it is concave up. And if you are asking me that why in that case the profile is used to be this parabolic nature, why parabolic, or it is mostly a logarithmic kind of profile was there. Here it is somewhat a parabolic behavior is there, so that we can simply go for the solution of the heat equation, energy balance equation in higher order terms, and we can get it here. It is out of the scope of this GATE syllabus, but if you people feel like that you want to know why this profile is in this way or in this particular manner, that we can have doubt clearing sessions on an elaborative approach to understand why these things are happening. So we understood the temperature profile, but for both the parallel flow and counter flow things. If this is the case in which there is the mass flow rate is happening or the thing is going to happen, and this is the manner. Supposing if we will move on to a very new thing, that is a phase change process. Phase changing is taking place. So suppose if we'll move on to a very good phase changing example, there is the case where x equals to 0 to x equals to L, we are extracting heat from a high temperature object that takes place in condenser. So in the condenser, what will happen? There will be a high temperature fluid. So here THI and THE, it will be a straight line. Why? The reason is because phase change takes place at constant pressure and temperature, two property rule that we have analyzed from the thermodynamics. Here, if we are supplying a colder fluid, it is absorbing heat and it is getting condensed, then the profile of the colder fluid will increase. Here it can be a parallel flow or a counter flow. Supposing if we are taking a parallel flow, TCI, TCE, this is what the temperature profile for a condenser will look like. Now moving towards the same thing, we will analyze the heat exchanger in which the phase change is taking place from increasing the heat from low to high by supplying a higher fluid. So here the best example for this thing will be for the system from x equals to 0 to x equals to L. Here what will happen, that there will be a very hot object that will be from a high temperature to low temperature, THI, THE, and there will be a temperature profile in this way where the temperature will be flowing from TCI, TCE, and this is absorbing heat from there, and this thing comes under the application that we analyze in a evaporator. Here also phase change takes place at constant pressure and temperature, and these are the temperature profile where the system undergoes phase change processes. So for the parallel flow, counter flow and phase change processes, what all thing that two primary thing that have come into our picture is that the temperature distribution in a heat exchanger, whether it be a parallel flow or counter flow or phase change, if we will do a small recapitulation of the same. See, this is a parallel flow, the temperature profile. This is the counter flow temperature profile, and in phase change process the temperature profile. What we understood, that the temperature that is being transferred or being exchanged within a heat exchanger is a function of distance and time. So primarily temperature in a heat exchanger is a spatio-temporal parameter. So to understand or analyze the heat distribution within a heat exchanger, we have to take into consideration both its impact on the length and on time. That is, it's an instantaneous phenomenon that changes abruptly with the passage at each sections. So from heat exchanger analysis to this temperature distribution, we concluded that the temperature within a heat exchanger is a function of distance and time. Therefore, while analyzing the heat exchanger, a very important term coming to picture that we call mean temperature difference, MTD, mean temperature difference. So what is this mean temperature difference? Supposing if we have a system and this system is transferring heat from suppose temperature T1 to T2, and in this overall system a temperature change is happening. So to analyze the heat transfer rate or the thermodynamic aspect or the overall heat transfer aspect of this heat exchanger, I need to study a mean temperature difference that is forming across this heat exchanger. To analyze that, a term mean temperature difference comes into picture. This mean temperature difference is primarily categorized into two parts. That first one is arithmetic mean difference, and logarithmic mean difference. So arithmetic mean difference is a quite low accurate temperature difference that we consider while analyzing the heat exchanger part, and arithmetic mean temperature difference is expressed as Thi plus Th exit divided by 2 minus T cold inlet plus T cold exit by 2, the difference of the average of the hot and cold fluid inlet and outlet temperature. But logarithmic mean temperature difference, why this is important? Because if we will do a recapitulation of the previous things as I have discussed, we can see it is mostly or merely a logarithmic profile that we can observe for a heat exchanger. So in order for that, the logarithmic mean temperature difference brings a very good aspect to analyze the mean temperature difference. So the logarithmic mean temperature difference equation LMTD is del Ti minus del Te divided by ln del Ti by del Te. So LMTD, it is expressed as del Ti minus del Te by ln del Ti by del T. So this formula is well good for both parallel and counter flow. So now move on to analyze what is this del Ti del Te. So if we will initially move on to a parallel flow heat exchanger. This is the inlet section, this is the exit section. The difference in the temperature for this inlet section is del Ti, and the difference in the temperature for this exit section is the del Te. So here the del Ti for parallel flow is Thi minus Tci, and del Te for parallel flow is The minus Tce. Practically, we can see this The and Tce can never meet or can never be at the same point. That's why the system, because the reason is that the system of parallel flows are quite irreversible in nature. It has high entropy. Entropy leads to the high degree of randomness in the system, and it arises to the irreversibility. Now moving towards the counter flow heat exchanger. Here if we will move, the del Ti will be same, the temperature difference at the inlet, that is Thi minus Tce, and here delta T exit will be The minus Tci. So if we will substitute this thing into this LMTD equation, what will we get? We will get that LMTD for parallel flow will be Thi minus Tci minus The minus Tce. So what will be it? Let's move on and do a simplified image to analyze the same. If it is a parallel flow, so both will be in the same direction. THI, THE, TCI, TCE, LMTD will be delta T. THI minus TCI minus THE minus TCE divided by ln THI minus TCI by THE minus TCE. Similarly, if we will go for this LMTD counterflow, what will it come? The drawing, it will be THI, THE, TCI, TCE, excuse me, it will be equals to THI minus TCE, THI minus TCE whole subtract THE minus TCI, THE minus TCI divided by ln THI minus TCE divided by THE minus TCI. So this is the LMTD equation to estimate the logarithmic mean temperature difference for a parallel flow and for a counter flow. And here we have analyzed the trick how to remember the LMTD. So remember these two graphs for the parallel flow and counter flow, and a generalized equation del Ti minus del Te divided by ln del Ti by del Te. So this is what your LMTD shows, logarithmic mean temperature difference. So we have analyzed the logarithmic mean temperature difference and arithmetic mean temperature difference. Here we will solve some of the previous year questions. So now let's move on to a question that has come in the year 2020. There the question is, a fluid is heated from 40 degrees Celsius to 60 degrees Celsius in countercurrent double pipe heat exchanger. Hot fluid enters at 100 degree, exit at 70 degree. Calculate the LMTD. And it is a 2-mark question that has come in 2020 chemical engineering. So simple. It is showing a double pipe heat exchanger. It is a 2020 GATE chemical engineering question. Double pipe heat exchanger, counter current, that means hot, cold. Hot enters at 100 degrees Celsius and exit at 70 degrees Celsius. Cold enter at 40 degrees Celsius and exit at 60 degrees Celsius. So here what will be the delta Ti, that is 100 minus 60 equals to 40. What will be the delta Te, that is 70 minus 40, that is 30. Then what is LMTD? The LMTD is 40 minus 30 by ln 40 by 30. So this is equals to 10 by ln 4 by 3. So that what will come around 34.76 degree Celsius. See how simple and direct question it was from this LMTD estimation. Now we'll move on to another question that has come in 2019. It's a quite tricky one but very simple. It says that there is a stream A. 2019 GATE question. There is a stream A. Stream A, the specific heat is 2000. What will be the unit of specific heat? Joule per kg Kelvin. It has given the specific heat and the temperature. It shows that stream A enter at 90 degrees Celsius and exit at 45 degrees Celsius. Similarly, stream B, it is giving the specific heat is 1000 joule per kg Kelvin. Here it is entering at 40 degrees Celsius. So here it asks us to calculate the arithmetic mean temperature difference, where U, the overall heat transfer coefficient, is 250 watt per meter square Kelvin. and the mass flow rate of stream B is 1 kg per second. Another thing, it has given area of the heat exchanger to be 8 meter square. Hot fluid Cp is given, delta T is given. Cold fluid mCp is given. In delta T, one parameter is missing. Overall heat transfer coefficient comes into picture. Then it has asked us that what will be the net UA delta T, where delta T is the arithmetic mean temperature difference. We have to estimate what will be the heat. Here, see one thing. Question will come into mind, what this convect overall heat transfer coefficient U stands for, and why I haven't discussed it previously and suddenly it is coming into the picture. I have kept this parameter safe for this problem. So here comes a thing, overall heat transfer coefficient. Are you guys clear about or acquainted with the terminology K, that is the thermal conductivity? So thermal conductivity is a material property, watt per meter Kelvin. It says how a material conducts heat through it. Similarly, for a flowing fluid, we know from the Newton's law of cooling, Q equals to HA delta T. What is H? H is the convective heat transfer coefficient. In the heat exchanger, two different fluids are flowing. Supposing if this is a cross section, here one fluid is flowing and here another fluid is flowing. So it will be having some H, it will be having some H. So the overall heat transfer coefficient 1 by U is equals to 1 by H1 plus 1 by H2. So it sum up the overall convective heat transfer coefficient that is flowing within the system. So U is given. You know that Q equals to UA delta T AMTD. AMTD equation is also known to you. That is, what is that? THI plus THE by 2 minus TCI plus TCE divided by 2. Okay, this is known to you. Again, this same Q is equals to mCp hot 90 minus 45. This is also equals to mCp cold 40 x minus 40. So we will know the magnitude of Q only if we can solve this equation. Here there is one equation, another equation, two equation and two unknowns are there. We can easily solve it. So this THI plus THE by 2 minus this thing is equals to here mCpH, this thing. In these two equations we found out here. Okay, so in these two equations, first we have to calculate the value that is not known to us. So the first value that is not known to us is the TCE. So how we will approach to understand the TCE? So to analyze the magnitude of TCE, initially what we'll have to do, that we have to equate any of these two equations. So what equation we will take at first? If we will see here, in this part everything is known to us. In this part everything is known to us, only this TCE is unknown. So if we will equate these two equations, TCE is unknown to us. So at first what we will do, we will equate THI plus THE by 2, that is 90 plus 45 by 2, that is 135 by 2 minus x minus x plus 40 by 2 is equals to 1 into 1000 mCp x minus 40. So from here I will get the value of x. Once I get the value of x, I will put the value of x here. I can calculate the q. From the Q, I can calculate the mass flow rate of hot fluid. So overall, by solving this one equation, we develop the fundamental to analyze the overall heat transfer coefficient. What is that, why it is taken, and how by using this Q equals to UA delta T LMTD and this first law of thermodynamics and equating it, we can solve this problem. Hope I am clear to all of you till this LMTD part. Have a good day.